Hello everyone and welcome back to Nunley Math. I'm Aaron Nunley. Thank you so much for joining me here today as we talk about algebraic inequalities. Now in my class we have just completed our unit on algebraic equations and expressions, and those ideas and concepts relate very closely to what we're going to do here today. So I kind of tag this onto the end of that unit as sort of an additional lesson. We do want to look at how this is connected to equations, but we also want to discuss some ways in which algebraic inequalities differ from algebraic equations. So what I'm going to do is go ahead and put up a set of number lines for you. And for each of those number lines, we have an algebraic inequality. This one says x is greater than 5. This one says negative x is less than negative 5. And for our purposes today, we're going to say that the domain for x, or the possible values for x, can be any real number. In earlier lessons in my class, we talked about how x could be real numbers or how it could be limited to integers or something like that. For today, we're going to say any real number could be a possible answer to this question. So what I would like you to do is I want you to think about what numbers that are real numbers could we plug into this inequality that would make this into a true statement. And I'd recommend pausing the video, drawing your own number line, and trying to find all of those on your own. I'm going to assume that if you wanted to do that, you already have, and I'm going to provide some examples for you. If x was a 6, I happen to know that 6 is greater than 5. So the number 6 would make this into a true statement. So I'm going to represent that as a dot above my number line. Now some teachers put them as dots on the number line, but I find, especially when my students are using pencils, that makes them hard to read. So I always draw them above the number line. I also happen to know that 7 would make this true because 7 is greater than 5. So I put a dot above the 7. I happen to know that 8 is greater than 5. And I happen to know that 9 is greater than 5, and that 10 is greater than 5. Now, keep in mind that there are lots of decimal values that are in between these numbers that are also true. So I could have just as easily have said 6.5 is greater than 5, or 7 3/4 is greater than 5. In fact, any number from this point on my number line all the way on to forever would work. If I were to pick numbers over here like 0, 0 is not greater than 5, so I would leave it out. 1 is not greater than 5, so I would leave it out. The big question arises as to whether 5 should be included or should be left out. Hopefully you realize that 5 is not greater than 5, and so it would be left out. So an open circle represents leaving this value out, and then all the decimals and values between 5 and 6 are included, as is everything else to the right. So I draw an open circle here at 5, meaning leave it out, and then an arrow to the right showing that it goes on forever. Hopefully most of us are pretty good at that, or if we've not seen that before, at least it makes sense for us. What's a little more complicated is this negative x is less than negative 5. We have to ask ourselves, what values could I put in for this x that would make this into a true statement? Again, I'm going to recommend you pause the video, try and come up with a few on your own, see if you can graph some of those before watching my explanation. Here's why this is tricky. If x is a 6, negative 6 is less than negative 5. So 6 is a solution. A lot of people get thrown off by this negative sign right here. This negative sign says no matter what we stick in for x, we're going to use its opposite. So the opposite of 6 would be negative 6, which is less than negative 5. If I were to plug a 7 into this inequality, negative 7 is also less than negative 5, so I graph it. Remember, the negative sign is always there. If I plug in an 8, negative 8 is smaller than negative 5, negative 9, negative 10, and so on and so forth. In fact, anything to the right of 5 on my number line is going to give me a solution that is less than negative 5. That kind of frustrates my students sometimes, because when we think of the numbers being less than negative 5, we typically think of the numbers over here on the left of the negative sign. But because we're using the opposite of our numbers, it's the really big numbers that would make this true. The opposite of these big numbers are the things that are going to be smaller than negative 5. For example, if I were to pick a negative 7, that would give us something interesting to talk about. Negative 7, if I were to plug it in, would be negative 7 is less than negative 5. Well, the opposite of negative 7 says 7 is less than negative 5. That is not true, so we could not put that in here. Again, 5 we're going to have to leave out, because if I were to plug in a 5, I would get negative 5 is less than negative 5, which is not true. Did you notice something strange? Up here, this greater than inequality and this less than inequality both have the exact same set of solutions. They both say leave out the 5 and use all the values to the right. Down here, leave out the 5 and use all the values to the right. A negative sign does some strange things to an inequality. Let's take a look at another set of examples. X is greater than or equal to a positive 2. Again, I'm going to recommend that you pause the video and you try and graph those on your own before watching my explanation. I'm going to go ahead and do this one a little faster than I did last time. Notice, in this case, because there's an equal sign, 2 is not greater than 2, but 2 is equal to 2. 3 is greater than 2. 4 is greater than 2. 5, everything from 2 to the right is going to work. 10 is greater than 2. So this is our set of solutions. But when I graph this one down here, which I assume you've paused the video and tried, I get this. X is less than or equal to 2. Notice the 2 is still included, but I'm picking the numbers to the left. 1 is less than 2. 2 is less than 2. 3, did I say that wrong? Negative 1 Here's another set of inequalities. I want you to pause the video and try and graph these on your own before watching my explanation. Notice this time I'm looking for things that are greater than 2 or equal to 2. I'm going to do them faster this time. Since we have the equal sign, we're going to color in the 2 because 2 is equal to 2. And then everything to the right is also going to work. 3 is greater than 2. 4 is greater than 2. 5 is greater than 2. And so you end up with an arrow that looks like this. But when I graph things that are less than or equal to 2, I include the 2, but then I include everything to the left. 1 is less than 2. 0 is less than 2. Negative 1 is less than 2. Negative 2. Negative 7 is less than 2. Everything on the left side of the 2 is going to be included. Which brings us to this one right here. Remember, we said negative signs do weird things to inequalities. So you're probably going to want to guess and check some points to see which one works before you come up with your solution. So I'm going to do that here. If I were to pick a 3, the opposite of 3 is negative 3, which is less than or equal to negative 2. So 3 is a possible solution. If I put in a 4, the opposite of 4, negative 4, is less than negative 2. And 5 works, and 6 works, and 7 works. In fact, everything over here to the right is going to work. It is important for me to point out that if I were to plug in a 2, the original equation has an equal sign in it, which mine typoed out. Negative 2 is equal to negative 2, so it should also be included. Notice there are lots of fractions and decimals that also work. Anything over here to the right is a solution to this inequality. Now, if I were to delete all my writing, I want you to compare these three graphs. Notice, as I switch to blue, notice that this first inequality and this last inequality give you the exact same set of solutions. And it has to do with the nature of this negative sign. In fact, If we say that x is greater than or equal to 2 and negative x is less than or equal to negative 2, if we say they have the same answers, we would say they have the same solution set. Keeping in mind that if we're talking about numbers that are greater than 2, when I look down here, those same numbers have opposites that are smaller than negative 2. That's because the things that are over here have opposites that are way back here. It's kind of confusing to think about the fact that things that are greater than 2 here have opposites that are way over here on the left, because we're essentially flipping those values over that 0. Now, this leads us to a rule or a pattern. If you have something like negative x is less than or equal to negative 2, you can use what's known as the property of inequality. The property of inequality that works much like the property of equality. And it says, I can do whatever I want in an equation as long as I do it on both sides. So, since I have a negative x, the identity property says that's the same as 1 times x. The identity property says times 1 doesn't do anything. And if I want to get rid of a times negative 1, I can divide both sides by negative 1. Remember, anything divided by itself becomes a 1, causing this to go away. But something really interesting happens here. If I divide by this negative 1 in an inequality, I'm changing from this form down here into this form up here. I'm getting rid of the negative sign. So when I do that, my inequality sign has to flip as well, giving us an answer of x is greater than or equal to positive 2. When we're working with negative signs in an inequality, anytime I multiply or divide by a negative number, I'm going to have to reverse this sign. That's the property of inequality. I can do anything I want to an equation as long as I do it on both sides. However, if I multiply or divide both sides by a negative number, I must reverse the inequality symbol. Now, what's tricky about this for most students is we don't just start flipping this anytime we want. There are specific times when we're going to flip this sign. And those specific times are if this denominator is a negative 1. If I divide both sides by a negative, then I flip. If I multiply both sides by a negative, then I flip. Any other time, I solve it just like I would any equation. So let's work a couple of these. This is an algebraic inequality. It looks very much like our equations did, except this sign is a greater than symbol. I'm going to solve it just like I did when solving equations before. I'm going to use the property of equality to get rid of the addition. Remember, negative 3 and positive 3 are opposites, meaning that's going to turn into a plus 0, and the identity property says I don't need to write that plus 0 down. Over here, I just do some computation. Again, this looks just like a single-step equation, except instead of an equal sign, we have a greater than symbol. How would we get rid of a times 8? Well, we divide both sides by 8. 8 divided by 8 is going to become a 1. The identity property says I don't need to write the 1 down. Negative 56 divided by 8 becomes negative 7. There's your solution. Notice that when I did this, my sign did not change. That's because at no point in my solving process did I multiply or divide by a negative. This works just like equations work. Now, one thing I do ask of my students most of the time is after they've found the solution, I do ask them to graph those solutions so we can see what those look like. I want everything greater than negative 7, but negative 7 is not greater than itself, so I use an open circle. Now, just like with equations, once I'm finished with this, there are ways for me to check and verify that my solutions are correct. What I would normally do is first of all check the endpoint by checking whether or not this negative 7 will actually give me the boundary between the two sides. So I use the equal sign. Is the negative 7 where they are equal? And I would substitute that in and simplify to see whether they match. So we know that negative 7 is the point where the two sides would be equal to one another. What we need to decide next is whether we have the correct side for greater than. One side will be greater, the other side will be less. That end point should be the equal. So I'm going to check the direction by plugging in any value along this right side. I happen to pick negative 5, which is right here. If my arrow is going the right direction, when I go to check this inequality, I should end up with a true statement at the end. 8 times negative 5 is negative 40. Add 3 is negative 37, which is in fact greater than negative 53. Notice there are two checks. One for the endpoint to see if that's where the values would be equal, and then one for the right side of the inequality to see whether we are pointing our arrow in the right direction. Keep in mind, negative 7 is not a solution because we left out the equal sign here, but it is important for us to know that that open circle is in the right spot. Here's another example for you. I'm going to do this one a little more quickly this time because we are relying very heavily on principles and properties we've used before. I'm going to recommend that you pause the video, try it on your own before watching me do this, but I'm going to start off by distributing 5 to everything in the parentheses. And then I'm going to use the property of inequality to get rid of the 160. Remember, 60 and negative 160 are going to make 0, and the identity property says I don't need to write that down. I now want to get rid of this times 5. I can either divide both sides by 5, or I can multiply both sides by the reciprocal or multiplicative inverse. Because I know 1/5 times 5 is going to be a 1, and negative 15 times 1/5 is going to be a negative 3. Notice once again, when I do this, that my inequality sign has not changed because I have not multiplied both sides by a negative. Don't let the fact that this number was negative throw you off. What I did to both sides was not negative. So we get x is less than or equal to negative 3. Once again, I'm going to require my students to graph this. Notice that it does have an equal sign, which means that we will have negative 3 in our answer, and we want those values that are smaller than negative 3. So negative 3 and all values to the left. Once again, we should check our answers. So I'm going to check my end point first. We said that negative 3 is our boundary where they should be equal. So I'm going to plug that in. Negative 3 plus 32 is 29. 5 times 29 is 145, which does work. I'm then going to check my direction, which means I can pick any point along this line to make sure that my arrow is going the right way. So I rewrite the problem. Let's plug in a negative 4. Right here, negative 4 is in the line, so it should work. Negative 4 plus 32 is 28. 5 times 28 is 140. 140 is less than or equal to 145, so we know our arrow is pointed in the right direction. Let's do one more of these. Again, pause the video. Try this on your own before watching me do it. I am going to start doing them faster and faster. I'm going to add x to both sides. I end up here. I'm going to add 21 to both sides. I end up here. And then I'm going to divide both sides by 5 and end up here. Notice on this last example, I multiplied by 1/5. In this example, I divided by 5. I go back and forth as to which I prefer. It really doesn't make a big difference. Here's something I want to make sure we notice, though. If 8 is smaller than x, that means x is bigger than 8. We generally like our x's to be on the left side of our inequality. Most of the time, that makes them less confusing for us. So make sure you take the time to go ahead and switch that. Remember, if 8 is smaller than x, then x must be bigger than 8. And then we'll graph our solutions. I know that the 8 is not greater than itself, but that is where my boundary will be. And since I'm looking for things that are bigger than 8, I'm going to be going to the right. Make sure you leave the 8 out with an open circle. As always, you do want to do a check here. So I rewrite the original problem. I want to test the end point, so I put my equal sign in here, and we want to know, would this equal 8? Remember, 8 is not a part of our solution, but we want to make sure it's in the right place anyway. So I substitute that in. I get 11 is equal to 32 minus 21, so it's 11 on both sides. My open circle is in the right location. I then pick any number to the right of that, and I check again. Once again, I end up with 11 is less than 19, which is true. Therefore, I know my answer is correct. Not too bad, right? Let's do a couple more that look a little bit different. Again, pause the video, try this on your own, and then watch me do it. I'm going to subtract 13 from both sides. I'm going to divide both sides by the negative 11. And then make sure you flip the sign. Now, I did this on purpose because I wanted you to remember that we only flip the sign if we multiply or divide by a negative. I intentionally picked examples a second ago where there was no flipping involved. And I did that on purpose because it's very easy for us to fall out of the habit of looking to flip our signs. And if you get out of the habit, eventually one of those problems will sneak up on you and you'll have to do a flip. Students tend to fall into one of two categories. They either flip everything or they flip nothing. You have to be careful to always be looking for whether or not the sign has to be flipped over. Since I divided by a negative, this greater than became a less than. X is less than 6. Again, I'm going to graph this a little faster. Less than 6 would be to the left. Since there's no equal sign, we're going to use an open circle, leaving it out. And then we're going to do our checks. Again, I want to know if the 6 is the boundary, even though it's left out. So I plug it in and I simplify. It is the correct boundary. And then I want to check to make sure my arrow is going the right direction. I can pick any number along that arrow. I picked a 0 because I thought it would be easy to compute with. And again, I get a true statement. 13 is bigger than negative 53, so I know my answers are correct. One last problem. Again, pause the video, try it on your own, and then watch me do it. I'm going to start by distributing that negative 9 to both of these. I'm going to use the property of inequality to subtract 18 from both sides. Divide both sides by negative 9. Notice I'm dividing by a negative, so I have to flip the sign. Only when I multiply or divide by a negative is the sign flip. But notice now my x is on the right side. If 10 is smaller than x, that means x is bigger than 10. Make sure when you're done with an inequality that you always have your variable on the left side. It makes it much easier when you go to graph your solutions. 10 is going to be an open circle because it cannot be bigger than itself, and it is an arrow going to the right. I'm not going to take the time to check this because we've already done several of those, and I don't want this video to get overly long, but hopefully that makes sense to you. The only thing that's different today is knowing when to flip or not flip the inequality. So make sure you're fully understanding that before you move on. Thank you so much for watching this video and for joining us here today. I hope that made perfect sense to you. I hope you all have the very, very best of luck. Take care of yourselves. Bye-bye.